that this concept of blockchain that actually evolved from different angles. So it is not like a kind of complete new technology that suddenly came. Rather, it is a kind of nice amalgamation of different concepts from different domains. So we have seen that the fundamental paper behind the design of Bitcoin by Satoshi Nakamoto that actually combined the concept from distributed system, the idea of using a hash chain for storing transactions in a tamper-proof manner, and then the concept of economics that to have a kind of economical balance of assets, and at the same time providing a kind of say remuneration to the participants who are participating in the block generation procedure. So through this different angle of technology, this Bitcoin, it effectively utilized the concept of a hash chain in a complete decentralized setting. But as I was mentioning earlier, that even in the paper by Satoshi Nakamoto, that concept of blockchain, means that terminology blockchain had not been mentioned. He or she, do not know, had used block and chain, the two different terms separately. Like somewhere he mentioned about forming the transactions or collecting the transactions in the form of blocks, and then connecting the blocks in the form of a chain. So that way, these two different terms, block and chain, has been used, but the term blockchain have not been used. So the terminology blockchain, it become popular after this blockchain, or rather Bitcoin became popular, and at the same time people started to deploy different kind of interesting applications on top of Bitcoin. So people gradually moved out of this cryptocurrency based concept and tried to think of utilizing the distributed ledger technology for different purposes. Right? And one of those prominent use cases where the developers thought of to use this concept of distributed ledger technology, or the concept of blockchain, whatever you say it, in the domain of automated execution of programs, or automated execution of code. So they used to call it as the smart contract. So the idea is something like that: any kind of contract that is written programmatically, that can be represented in the form of a state transition diagram, or in the form of a state machine, right? So what you can do that, say for example, here I have a very simple code. The first function is actually makes a payment. So it checks whether the sender account has sufficient amount of balance to make the payment equal to the amount. If so, it deduct the money from the sender account and add it to the receiver account. And the second function, deliver goods, what it does, that it takes the count of the goods or items that need to be delivered, and at the same time the price per count. And then it make a call to the pay function to check whether the payment is successful. If the payment is successful, then it schedule the logistics, that means schedule the transfer of the goods. So here it is a kind of automated way of putting up certain orders, where you can just put the orders, and then the vendor will check that whether the payment can be made. If the payment can be made, then you deliver the good. Well, so kind of automating the entire process. So this particular contract, or this particular piece of code, you can see that we can represent it in the form of a state transition diagram. So what we can do, that we can define the state with the variable sender account, receiver account, and account, where the initial state contained the sender account equal to I, receiver account equal to J, and count is equal to 0. Then the corresponding function, say deliver good, is called. Whenever the deliver good function is being called, during that time you check for the amount, or you make a call to the pay function, and the pay function is actually updating the state of this particular state transition diagram. Now, this piece of code can be executed in a decentralized way. So what I typically want that rather than executing the code to a common server where all the parties who are participating in this business they can see the output of the transactions and everything. I want to execute in a complete decentralized way. So my idea is that I do not want to use any kind of centralized server or any kind of centralized component that will maintain this kind of contracts. Rather, I would execute the contract in a complete decentralized way. So what we can do that we can actually put the state of execution in the blockchain. So every individual party or every individual participant, they can independently start executing the code. So that way, you can see that my basic premise behind the design of blockchain is that I need to initiate a transaction. So here the transaction can be the function calls which are making a state change. Say for example, make a function call to deliver good and make a function call to pay, which are the corresponding transactions. So these transactions are initiated. That means that someone requests for delivering the good. So whenever that request is being made, so what I typically do that I execute the function, well, and accordingly make a state change in the global state machine. Well, so that has been stored with the help of a distributed ledger technology. Now, what actually happens in a decentralized architecture that because every participating node, they are having a copy of that DLT on the blockchain, they can actually verify that whether the function have been executed correctly or not. So if some malicious node or if some attacker tries to execute the function in a tampered way, immediately that will be caught by looking into the state transition feature because the function is publicly available, so that can be validated by everyone. So this way of automated execution of contracts in a decentralized architecture that we typically call as a smart contract, and this concept of Bitcoin 2, it actually introduced this idea of smart contract in the form of Bitcoin scripts that we will see later on, that how the Bitcoin script actually support decentralized programmability that actually had been extended in the concept of blockchain. Now, let us see that how these blockchains are helping in the smart contract execution. Well, so assume that Jimmy and Emma, they want to execute some smart contract. So what they do that they first make an agreement that this is going to be my contract, and that is something off-chain. Well, so what you want to do that the execution of the smart contract that you want to make it automated. And how does it help? Say, for example, in case of a supply chain management ecosystem, whenever you are delivering the goods, the payment can be automated and the verification can be done in a complete automated way. So the example, if you can remember that I explained earlier in the context of giving you an use case for blockchain-based application. So you make this agreement off-chain, and after you are making this agreement off-chain, you submit this agreement through a blockchain network. Well, now while submitting this agreement in the blockchain network, what you can do that you can anonymize it with the help of your public key value. So what you can do, you can say that Jimmy uses his public key to submit the contract to the blockchain network. Emma, she uses her public key to submit the contract to the blockchain network. So what the community sees, they see that, well, two persons which are identified by their public key, they have submitted this smart contract and the smart contract matches. So that means both of them has agreed on this particular smart contract. But you see that whenever someone is submitting the smart contract or submitting the contract or the agreement on top of blockchain, they are not using their public names. Rather, they are using their public key, which is anonymized. So that way, for the world, they will not be able to see or they will not be able to understand that who has actually submitted the contract. Well, because remember that the property of the public key is that it belongs to a particular person, but a particular person can hold more than one public key. Well, so that way you can know the public key of a person, but just by knowing the public key, you cannot identify that who the corresponding person is. Well, so that way the contract or the agreement that is being submitted to the blockchain network, it remains anonymized. Well, and then everyone in the network, they can see and validate the execution step of that contract. Well, so that way it is helping the automated execution of the contract in a decentralized environment. Right. So one of the popular smart contract application that have been built up on top of Ethereum smart contract is this CryptoKitties. So CryptoKitties is an interesting game where you can it is a kind of environment of digital cat in a virtual world. So you can buy cats, you can feed them, well, and then you can grow them, well. So then you can also sell a cat. So that way, this CryptoKitties, this particular application was actually very popular, and that was a game which was developed on top of Ethereum smart contract. So if you want to get a feel about how a decentralized gaming typically works, you can try it out. So the interesting fact about this CryptoKitties is that we do not have any game server that is hosting the game. Well, rather this game has been hosted in a complete decentralized way. Whenever you are joining the network as a player, so your machine is contributing in hosting the game. Well, basically, what actually happens that the state of the cats, so all the cats which are there in the system, so the state of the cats are basically stored in a blockchain. Well, and over the time that cat gets evolved, and whenever say you are selling the cat to someone, that state is getting updated in the blockchain. Similarly, whenever you are making certain changes in the cat, well, say for example, you are putting up a necklace to the cat, and that kind of things are getting updated as a state in the corresponding blockchain. Fine. Fine. So with this invention of blockchain, well, any question up to this point about the smart contract or the smart contract execution?
Sir, in case of the example you gave about Jimmy and Emma, so suppose there is James who also wants to execute the same smart contract, then what he should do? So will Jimmy add James account to smart contract, or is there some easier way to execute
So
that?
you are saying that once I have submitted the contract, if I want to make any change in the contract,
Yes,
right?
no, sir. If another person wants to execute that same smart contract in the blockchain network, how will that happen?
So there are two things. One is that these contracts are basically a kind of agreement between two or more parties. Well, so when these parties are coming to an agreement, well, they will come to in that agreement off chain. Well, so it is something like that. You are preparing the agreement paper that if you send me this much of goods, then I will pay you this much of money. Such kind of agreement. So these agreements are prepared offline, and then these agreements are uploaded in the blockchain. So what blockchain actually helps? The blockchain helps in automated execution in that agreement. Well, now if and the way this blockchain is helping in that automated execution of the agreement, it is something like that. Whenever certain transactions are getting initiated corresponding to that agreement, say for example, the earlier code that I have shown, that where you have the call to the function called deliver goods, which is a kind of transactions which is getting executed. So whenever such kind of transaction is getting executed during that time, the nodes in the blockchain network, they can actually execute the transaction themselves because everyone has the availability of that code. The code has been submitted to the smart contract, and they can find out that what is going to be the correct next step if I execute that transaction. And they check that whether that particular state is there in the that particular state is there in the contract or not. Okay, so this is something the way the contracts get executed. Now the thing is that if say the initial contract was between Jimmy and Emma, now say Bob wants to participate in that contract, so then he wants to join to that agreement, he wants to come to that business. So what you have to do, you need to redefine the contract. Well, now whenever you are redefining the contract, during redefining the contract, what you can do that you can actually initiate another transaction to redefining the contract. So you can initiate a transaction saying that, well, Bob is participating in that agreement and this is the kind of amendment to the code which is there when Bob is joining in the network. Well, so that way everyone in the network, they will be able to see that, well, earlier the contract was between Jimmy and Emma, now Bob has joined and the contract got updated. Well, so every step that you want to execute on that contract, you need to initiate a transaction on top of that and make it visible to everyone in the network so that everyone can collectively validate that the contract is getting executed with the correct sequence of state transitions.
Yes, sir. Got it. Thank you, sir.
Okay.
Sir, can you explain again why using public key encryption we can anonymize the contracts actually?
So whenever you are submitting the contract, so for example, whenever I am submitting the contract, I am not submitting the contract tonight. I am not that I am saying, so this is the contract that is submitted. What I am doing that I am generating the public, and after generating the public key, I am submitting the contract. Now you start that based.
Sir, your voice is breaking a lot. You're not clear, sir.
Yes, okay. Can you please tell?
Sir, you were clear a while earlier, but your voice is breaking now.
Okay, now is it okay? Because I think that some noise was coming from some other persons.
Yeah, it's okay now.
Okay, let me also
hear the answer you give.
turn off the video. That will help. Okay, so what happens that whenever you are submitting a contract, while submitting that particular contract, during that time, I'm saying that, well, this contract have been associated with this public key. Well, now if I submit a contract with respect to a public key, it is difficult for the world to know that who is the holder of that public key. Okay. So that is the kind of reason that the entire contract get anonymized with the help of that public key. You got the point?
But sir, isn't there the whole point of public key encryption, we can actually establish the relation between who holds the public key and the public key actually. So there in the public world there should be a list, right, which with the user and the public key.
See, that is in terms of whenever you are saying it in terms of digital signatures. Well, so just after this particular my part of talk is over, Professor Sural will take the control and he will be explaining that how the things get executed in a typical Bitcoin network. There you will see that every transactions that have been put in the form of one public key to another public key. Okay, so it is something like that. Public key X is making a transaction to public key Y. Well, so the world will only be able to see that public key X is sending the transaction to public key Y, and that way, public key X is sending the transaction to public key Y, and that way everyone will be able to see only that public key. Okay, so they will not be able to see that who is actually transferring the money, whether Sandip is transferring the money to Shamik or something else. Well, so that way the anonymity gets preserved. So the actual name of the person is not revealed. Now, the idea is something like this, that whenever you try to get hold of that transaction, so whenever you want to try to get that, well, I am Sandip, I am holding a public PX and I want to claim the ownership of that transactions, I can do that with the help of my private. Okay. So you will see that in the context of Bitcoin, that how these typical things actually works. Okay.
Okay, sir.
Well, so with this particular concept of public key encryption and utilizing that particular thing for smart contract executions in an automated way, people started think of blockchain in a broader context. Okay, so what people have seen that, well, this entire blockchain network that was particularly used for Bitcoin or Ethereum, which typically used consensus algorithms like proof of work, and later on there was multiple deviations from that proof of work, and there was advanced version of different other open consensus algorithms. So we'll discuss that later on. But this proof of work consensus algorithm, it made the blockchain popular, and people seen that it works good in an open network. So for a kind of cryptocurrency based applications or kind of applications that are developed on top of Ethereum based platform, it works good for those kind of architecture. Well, but one of the major problem of such kind of system is that the transaction latency is very high. Okay, why that is so, we'll see it later on while we are going to details of it. Well, so typically in case of Bitcoin network, it takes around 10 minutes for a block commitment. Well, and in case of Ethereum, it is a few seconds to few minutes, depending on the cost that you pay for executing your transactions. So that way, this kind of model is very slow to converge. Okay, so the transaction doesn't get executed immediately. Well, it takes some time for the transactions to get executed. Now the question comes that, can we think of any other blockchain applications beyond cryptocurrency? Well, and the major bottleneck which was there, that the high latency, it makes this proof of work unsuitable for most of the real-time applications. Well, so because the transaction commitment latency is very high, you cannot use it for kind of real-time application. It is good for this kind of cryptocurrency and kind of decentralized applications that you are trying to build up. But for the industrial applications or the kind of, say, applications like supply chain management, where the responses need to be very fast, for that kind of applications, it is not suitable. But the interesting fact is that many decentralized applications do not demand an open environment. Well, so for example, if you think of a food supply chain, well, or the KYC validation, trade financing, well, for such kind of application, you see that there are some fixed number of participants who will be there. That number may be something like 100 or 200, but you know who is going to participate there. Well, so for example, I am not going to participate directly in a kind of supply chain management. So there would be specific vendors, specific distributors. Well, and for specific supply chain network, those vendors, distributors, suppliers, they are fixed. Well, so for example, for a typical, say, this food supply chain. So for example, this vegetables supply chain management, that has one set of vendors, suppliers who are participating in that business. Whereas whenever you are going to the supply chain management for medicines and drugs, there are separate vendors. Well, but those vendors, suppliers, they are predefined. Okay, so they basically form a kind of closed network. It is not an entirely open network like the one which a cryptocurrency application demands. Well, now the question comes that can we support trustless decentralized on top of a closed network? Okay, and from there this idea of blockchain tree comes into practice. Well, so what does it means that, well, I would like to automate to relate it to the initial applications of oil and natural gas supply chain architecture that we talked about, that everyone is competitor to others. So that HPCL is a competitor to IOCL. Well, but they want to share certain kind of information. Well, so they do not trust each other, but still they want to share the information. So in such kind of architecture, what we can do that we can run smart contracts among themselves. Well, and these smart contract executions will ensure that the corresponding transactions are executed in a reliable and in a tamper-proof way. Well, and the core idea here is that we are going to run this smart contract among a set of organizations who know each other, but they do not trust each other. Okay. So the advantage of running such kind of a blockchain network within a closed network is that, first of all, we can go back to the classical distributed consensus protocols. Well, because if you remember that we moved to this proof of work type of consensus algorithm because our network was open. In an open network, I cannot use a message passing based consensus algorithm. But whenever I'm saying that I'm back to a closed network, within a closed network, I can run such kind of consensus algorithms which are based on message passing. So I can still use the classical distributed consensus protocols for a closed network. Well, and the classical distributed consensus protocols are known to be to have low latency for commitment and high transaction throughput. Right? And what we can do that one of the major disadvantage of Bitcoin type of network is that to mine a new block in a Bitcoin network, you need to invest a significant amount of resources because it is a kind of challenge response based architecture where you need to find out that nonce for a corresponding hash, and to find out that nonce you need to invest a significant amount of computing power. Well, so that way there was a criticism on Bitcoin network that Bitcoin is not very power efficient. Rather, it is a kind of extremely power hungry application. So to mine the kind of proofs for validation of a newly generated block, you are wasting a lot of power. Well, and remember, in case of Bitcoin network, we'll discuss that consensus algorithm again later on in details. But because multiple miners are trying to mine the block simultaneously and only one of them will win at the end. So typically the mining power that is being invested by the other miners that get wasted. So that is the kind of criticism which is there. But whenever we are in a closed network, we do not need such kind of mining algorithm. Rather, what we can do that we can add the cryptographic technique on top of the distributed consensus protocol. One of those techniques is something called the witness cosigning that we'll see later on in detail. So witness cosigning basically means that to agree on a particular message or to agree on a particular transactions, multiple parties, they sign the message together. Well, so it is something like that say we are having a network of 11 people, and within that 11 people, if 6 of them signs a particular message, collectively signs a particular message, then that message becomes authenticated because maximum number of people in the group, they have signed the message. So this kind of idea is called the witness cosigning. So we can use that witness cosigning instead of the proof mining, and witness cosigning is a very power efficient approach in contrast to proof mining. So those kind of advantages we have. And that way we can utilize the smart contract on top of a closed network to support multiple advanced applications on top of blockchain. Okay, so from that particular concept, this idea of permission of the private blockchain emerged. So in case of a private blockchain or a permission blockchain, the participants are pre-authenticated and pre-authorized, but they can still behave maliciously. So that is why they do not trust each other. Now, in that case, you run a blockchain network and the smart contracts on top of the closed network. Well, so basically you are ensuring trusted computing among the participants. Well, so that way, if you just look into the way this concept of blockchain got evolved, so initially the idea was utilized for cryptocurrencies, and the path-breaking novelty that has been introduced there is to the invent of that open consensus algorithm, which actually supported that FLP impossibility theorem by giving more weightage on the liveness compared to safety. Well, so the classical distributed consensus algorithms have given weightage to the safety compared to liveness, but this Nakamoto consensus or the proof of work, it has provided more weightage to the liveness, and that way it was been able to develop an efficient consensus protocol for an open network. But when we had such kind of architecture, people started thinking of other innovative applications apart from cryptocurrencies, and they introduced this idea of smart contract, where you can execute the contracts or a program on a network in a complete decentralized way. And whenever you are executing a program on a network in a complete decentralized way, you get the advantage that certain things can be automated by executing those contracts. Well, so for example, in case of supply chain management, the transfer of goods, the agreement to transfer the goods and the corresponding agreement to transfer the money. Well, so those kind of process can be automated, and that can be tracked with the help of a blockchain network. And after that, when smart contract became popular with the development of this Ethereum platform and different kind of gaming applications that have been developed on top of the Ethereum network, people started thinking of that whether I can still use the smart contract technology in an enterprise setup. Okay. But in an enterprise setup, the major challenge was the latency, which was there for the Nakamoto consensus or the proof of work kind of algorithms. And that is the reason people started thinking of that, can I now revisit the classical distributed consensus algorithms in a closed environment, because typically this enterprise networks, it is not an open network like the cryptocurrency network, rather it is a kind of very closed network. The participants are pre-authenticated and pre-authorized. But the problem is that these participants are competitive to each other, so that way they can behave maliciously, and when they can behave maliciously, now, whenever such kind of architecture is coming, we move to the idea of permission model of blockchain, where this blockchain is executed on top of a private network or a closed network with the help of the classical distributed consensus algorithms, but we can be able to execute the smart contracts on top of that. Well, so this gives you a kind of brief idea about how this concept of blockchain has evolved over time and how it has introduced different kind of concept within its technology. Later on, we are going to discuss the details of it. So, for example, we are going to discuss the details of these different kind of consensus algorithms which are used in the open blockchain network as well as in the closed or the private blockchain network. And then we are going to see that what are the different kind of smart contract execution model, how you can build up your own smart contract and execute that on top of a blockchain network. Okay. Now, I think we are going to discuss about the basic idea of this Bitcoin blockchain. So certain questions that few of you have asked for, that is going to clear by then, that how this anonymity is being preserved with the help of the public key. You can see that how it is being stored within the Bitcoin blockchain, that you cannot identify what is the origin of the transaction, but still you can validate the transaction. Well, with the help of that public key cryptography based anonymity platform anonymity architecture. So Professor Sural is going to discuss about those parts. So if you have any question till now, otherwise I'm handing it over to Professor Sural.
Yeah, thanks, Shandip. If anyone has any question to Professor Chakraborty, you can ask. Otherwise, I will start. Okay, Professor Chakraborty, if you stop sharing, then I will start sharing.
I already done it. Yeah. No.
Okay. Thanks. Okay. So what we'll do now is that we'll talk about the content, and these discussions will typically be referring to Bitcoin, and some of these could be referring to a relatively earlier version of Bitcoin, and that is because the versions also keep changing from time to time, making certain minor or major modifications. Okay. And one can always go through the detailed literature to get the updated information. So let us see that some of the important concepts which we'll explain with respect to Bitcoin, and similar concepts are also valid for other networks like Ethereum. And part of these this Ethereum and as we have mentioned, Hyperledger, which are permissioned blockchains, we'll also cover during our tutorials. Essentially, we have already discussed this part, that it is a platform for executing transactional services, okay, and spanned over multiple organizations or individuals who may not or they did not trust each other. The point here is that the goal was to set up the network where the whole operation will be done in a peer-to-peer mode and in a completely decentralized manner. So there should not be any way of trying to control or intervene, and the whole thing would also run in an automated manner. That means there is no one who is centrally controlling it or monitoring it, whether the system is working as expected. And most of the operations, including updates, are also automated in some sense, which we'll discuss. Okay. And of course, as we have mentioned, it is an append-only shared ledger of digitally signed and encrypted transactions, and which is, of course, has to be replicated across a network of peer nodes. The term ledger we have used before, we are using again. And just to give you an idea, ledger is something like, say, your passbook, okay, in your bank. So if you see the passbook, they make some entries, right? So it is only that you can append to it. You cannot tell the bank people that, see, there is an incorrect entry, please go and correct it, and they will strike through and make changes. Not, of course, in your passbook, but also in their own records also they cannot do it. So if by mistake, say, they transferred money from your account, say 100 rupees to another account, okay, but it was not supposed to be done, so they cannot go back and delete that entry. What they have to do is that they have to make a counter entry that will give you back that 100 rupees. Okay, so suppose it was supposed to be deducted from my account, but instead got deducted from your account. Now when they settle it, what they will do is that they will give you back the 100 rupees. They cannot delete that entry from their records. Okay, so this is like a ledger where things can only get appended. So here, now when you talk about a distributed ledger, you mean that it will be available in a large number of peer-to-peer nodes, and the whole thing will be happening in a completely decentralized manner. Okay, and this diagram, of course, also we have seen. So first we'll focus on for a block the header part, and then we'll talk about the transactions. Okay, so in a block, as we see here, we have these maybe block numbers 51, 52, 53, and there is something in the header which we are showing as proof of work, and there are more details as I will cover. And then there are some transactions which are also showing some, of course, as such non-readable values. So we'll see what part of that is public key and or hash of the public key and the transactions and so on. So first thing is that these transactions will be digitally signed and encrypted, and one can verify these transactions. So any peer, any node who is participating can do the verification. And of course, the security is provided by cryptography, which we have already studied, which ensures that participants can only view information that they are authorized to see. So, of course, that when it is a public permissionless blockchain, one will be able to see everything. Okay, if there is some private blockchain and permission, so those terms will look into more detail, that whether you can read everything or you can also create the block. So there might be a slight variation in the definition about what is a permissioned blockchain and what is a private blockchain, and a combination of these two. But these blockchains that we talk about initially, the Bitcoin or the Ethereum, these are what are called public permissionless blockchain. Means anybody can see and anybody can write. Okay. So that is the context in which we are discussing these block structures. Okay. Now, structure of a block, it is a container data structure, and that contains a series of transactions. Okay. So there will be several transactions in a block, and in Bitcoin, a block. So we are now focusing on Bitcoin. A block can contain more than 500 transactions on average. And I mean, there could be some 1,000 transactions. The average size of a block, it was set by Nakamoto as 1 megabyte. There have been some discussions of making it grow to a larger size, and there have been many conflicting views on this, whether to increase the size, what are the issues if the size is increased, and if you just search for why this Bitcoin size, block size should be increased and why it should not be, you will get so many different comments on it that the participants will say why it is a good idea, why it's not so good idea, and so on. Of course, we understand that if there are the block size is larger, it would mean that a lot of transactions will be there in the same block. Okay, that is quite obvious, and that means that in one go, large number of transactions can be processed. But actual time for verification and propagation would be more, because then one has to, of course, while I can say possibly include say 10,000 transactions in one block, but I have to wait for 10,000 transactions to come. So there will be some latency also, so that just as I get 1,000 transactions, I create a block, it will not be like that. I have to have 10,000 transactions in a block. But then the effort of actually creating the block will be less. So instead of 10 such blocks to be created of 1,000 transactions each, I will have the effort to create only one block of size 10,000. Okay, so these are different pros and cons of having a larger or a smaller block size, and there have been a lot of debates about that. Let us not go into that. Now, two components of a block, as I said, block header and list of transactions. And as I mentioned, we'll first focus on the block header. Now, here is some important resource that you need to keep in mind, and also you will have to explore. So I am first clicking on this one, this btc.com slash btc/blocks, and I am also pasting it because you may not be getting this otherwise. So I'm pasting it in chat box. Okay, so I have gone to that btc.com, and why I went there is that whatever I am showing here, I would like to show it live also to you. So if you look at this btc.com, you will see that it talks about blocks. Okay. And there is indeed one more site, okay, which is the blockchain.com/explorer. And if you go to that site, also you will get similar stuff. And there actually you can get Bitcoin information, you can get Ethereum information, and so on. Okay, so you see that these are providing you information about all different types of blockchain. Okay. Now, if you look at Bitcoin here, if you see the latest blocks, okay, so whether it is in this one or in the other one, you will of course see the same information. Okay, and if you click on any one of these, so these are the blocks. So it means that starting from the first block, okay, that was mined by Nakamoto. Now the block number is the 697,493, and it is in real time. You are seeing it. Okay. That 697,493 was created 7 minutes. Time to do it was 7 minutes, and the previous one took 7 minutes, and some took 8, 14, and so on and so forth. Okay. Now, if you see on the right side, you see that these transactions again in real time these are coming in. So of course you notice certain things that see in every minute so many transactions are taking place that you can see, and there is something about the amount of transaction that is in Bitcoin. You will see, you will look into those details, but you see some of these values are very small. But of course, because one Bitcoin is pretty large value of USD as we have discussed, so the amount of transactions in USD is also shown next to it. Okay. Now, if we see at the latest block, so if I click on any one of them, okay, I see the details of that block. So what that block shows here, if you look at it, so there is a hash, okay, and then there are some details. So this part is all about the block header part, okay, and then you have all the transactions. If you look at the transactions, so you have the first transaction which talks about the new coin. So because this block was mined, the one who mined it for first, he got some payment, and this payment is this amount, okay, 6.25 Bitcoin. And what it actually means is that for mining this particular block, there is a price that you get, okay, and also for each of the transactions that are contained there also you will get some money. So there are two sources of income for a miner. Okay, miner means one who creates a block, and after that you can see all the transactions. The first transaction is the new block mining transaction. That means I created that and I got this payment myself. So that is the first transaction, and below that I have all sorts of these transactions, and you can see that there are so many pages of transactions. Okay. Now, if I go back and if I say go to say another transaction, another block a while back, which has got larger size. So if you see that there is this in the header, you have this block reward. So that is for mining this particular block. So that is, you see that it is roughly fixed at 6.25 Bitcoin. And then there is a fee reward, which is the fee for every transaction, which adds up over all the transactions to this one, and the miner gets the whole thing. So this is not the amount that is transferred from one party to another in a transaction. It is just that because I have spent my resource to mine a block, I get some fee. One is for mining the block, I get that 6.25 Bitcoin, and for each of the transactions, the ones who are carrying out those transactions, they are paying me a fee. So these are all adding up to this much. So the total you see is that 6.35 something, and you see that there are more than 10 pages of these kinds of transactions here. So there are several transactions, and see that there are quite a few transactions in this particular block. Okay, so that is to give you an idea about what goes in each block. Okay, and I will also paste this particular link, okay, so that you also can try it out later, okay. And maybe in the class also, if we get time, we'll do that. Okay, so that is the idea about what goes in this. Okay, and if we see here in this block, so the portions that are of interest to us, let me show it in the context of this particular block. Okay, so this part is the header, as I said, and you see this height basically means that what is the block number starting from the first block. Okay, that is also called the height. It has got something like block size and stripe size and so on. So there are different things here. The points that are of importance is the timestamp. Okay, so there is a timestamp, and this timestamp that you see here, that is in our local time. You see 1250 was when it was mined, and if you just hover your cursor, so you get the time in UTC plus 0, because of course otherwise this time will be varying from one machine to another from wherever you are accessing. And the other point to note is this Merkle root. We have talked so much about the Merkle root, so you see that the Merkle root is stored here, and there is a version. Okay, version means that you are using a particular version of the software, so that version also is an important component. And the bits, actually this bits tells us about the difficulty level, that is the number of zeros, as we have mentioned, that should be there in the hash. Okay, And the nonce is what basically the miner finally had to come up with this nonce so that the hash that we get, and what is that hash? Here is that block hash. And that block hash should have the property that it has certain number of leading zeros. And how many number of leading zeros? That can be computed from these bits, this attribute of the block header. And if you see here, there are several such zeros here. So of course, you can see that this notion of leading zeros is important. And why not some more zeros? It is because that the current bits, whatever we have, that specifies the required minimum number of zeros. And this one actually satisfies that minimum number. So this hash is a valid hash for this block. And how was this hash obtained? It was obtained by hashing some of the components of this header, of which the nonce was missing. So the miner had to actually come up with this nonce in order to get a hash for the whole such pieces of information. That resulted in this hash with certain number of required number of leading zeros, and that required number is specified through this number of bits. Okay. So what I will do is that I will next tell you what is there that is required for doing the hashing. So some metadata already I have mentioned, that previous block hash. So that is used for calculating the hash of the current block. Okay. And linking them together, as we have seen here, that from one block we connect in the other block using its hash and so on. So that makes it tamper proof, so that if we change in one, we'll have to change it in all other places as well. So this is what we have seen this diagram before. And so if we say that the desired hash will have this number of at least leading zeros, so we have to have a desired hash to get to this particular value. So you see that finding that nonce is what is called mining. Okay. So the mining term is basically the mechanism to generate the hash. Okay. And it has to be complicated enough so that the blockchain becomes tamper proof. Otherwise, one can keep changing the block details and change its hash, and then change the hash of the next block, which refers to this one. Okay, and the next and the next, and if one could do that pretty easily, so one could tamper with the entire blockchain, starting from a block which contains a transaction. Suppose I wanted to change the value of transaction from 100 Bitcoin to 50 Bitcoin. I could change and later on change, and then change and reset all the hashes. Then nobody will be able to detect. Okay, so the point is that this mining step has to be really, really difficult. Okay, so the header also contains mining statistics, so timestamp, nonce, and difficulty. Now, if you see that this in this, let me show it with respect to block. Okay, so if you see the difficulty, okay, so here if you see the difficulty is mentioned here in this btc.com, you can see that difficulty is mentioned in some 15.56T, which was the theory difficulty, and the actual difficulty was something different. And here, if you see the block chain.com explorer, you see that the difficulty is given as a number. Okay, not a number, a value with some decimal values also. Okay, now what does it mean? Okay, let us see here. So what this concept is very, very interesting. That when this Bitcoin was started by Satoshi, the idea was that every block one should be able to mine with in about 10 minutes of time. Okay. Now you see that when this Bitcoin was started, then we could do hashes at a certain rate, because all that you need in order to mine a block is to be able to find a nonce so that the hash would match with the required minimum number of zeros. Okay, so that means as we can possibly try is that I could actually try a nonce value of 0 and see whether it is matching, and if not, then 1, and so on. But of course, one will not do it like that. One would actually be doing it randomly and so on. But effectively, that means that you need some computing power to carry out those trials, okay, and at some point of time you will be hitting the required hash which has these properties. But of course, then you see that what kind of computing power we had maybe 7 years back, okay, we or 5 years back or 3 years back, we are having more computing power these days. Okay, so if that number of leading zeros is kept fixed over a period of time, then what will happen is that after we have more computing power, we'll be able to mine each block very, very fast. So instead of 10 minutes, I could do it in 1 minute also. Okay, but the goal is that we don't want it to be less than 10 minutes for certain reasons. So of course, to ensure that it cannot be done so fast, because then someone who is able to tamper will be able to tamper all these things very quickly. Okay, so why 10 minutes? There are a lot of debates, and it was something that Satoshi had suggested, and we stick to that. Now, in order to do that, we always have 10 minutes in spite of the computing power increasing over a period of time. What can be done? What is done is basically the difficulty level over a period of time, it is increased. Okay, so difficulty is something like this. As we said, that there should be so many leading zeros, right? So if we increase more number of leading zeros, then the space is such that my possible hashes, that space is very limited. I have to give more effort to actually find it. Okay, a typical analogy is that, say, if you are in a room and if you are given say a football and a tennis ball, and you are told to find all the items which are less than the tennis ball, and in contrast all the items which are less than the size of the football, so it will be more difficult to find all the items which are less than the size of the tennis ball. Okay, similarly here, that difficulty is set in such a way that it should be having so many number of leading zeros, and as we progress, the number of leading zeros that are there, that keep increasing. So the first one was having the if you see that in this slide here, so you see that it only had 3, 3, 6, and 2, 8 leading zeros. Okay, and now if we consider the current ones, it has possibly some 15 or so leading zeros. So this target is changed. Okay, so what it means is that somehow, as I said, that everything has to be done in an automated manner. So what is done is that this entire Bitcoin network, it keeps tracking how much time it was taking to mine the blocks, and that is what we are seeing here, how much time it took to mine the blocks. Okay, so if we see this list here, okay, so we could see that at what time these were mined, and you could figure out that these were mined in say 8 minutes or sometimes 9 minutes or so. And accordingly, what happens is that the difficulty level will be adjusted, and it is adjusted over average time it takes in mining blocks over a period of 2 weeks and so on. Okay, so overall the concept is that the whole thing works in an autonomous manner, where the difficulty level is also adjusted based on the rate at which the blocks are getting mined. Now, in fact, there is this point also you have to understand, that when I said that people are using hardware for mining, it is not that you can do it in your laptop running maybe some Intel CPU and a GeForce card. These are the kinds of hardware firms that people are using in order to mine the Bitcoin blocks. Okay, so they need a huge amount of resource actually. Okay, and also what happens is that if we see that the difficulty level, I'll explain about the difficulty level in more detail in the next class. So difficulty level typically keeps increasing. Okay, so if we see for all time, you'll see that there is an increasing trend. But in July this year, there was a sharp drop. Okay, so that was something that was really noteworthy, and people try out the hashes, and in the entire Bitcoin network, if you see the total hash rate, if you see, it is like this. It is something like 120 million terahashes per second. So that is the total number of hashes that people are trying out and using this huge ASIC hardware. So all these are done in order to ensure that no one can actually tamper with it so easily. At the same time, the actual block mining time is somewhere limited to 10 minutes. Okay, so and that gets automatically adjusted even as the computing power available increases. that time also, the difficulty is adjusted so that the average mining time remains at 10 minutes. So I'll stop here, and in our tomorrow's class I'll discuss more details about what is this relationship between difficulty and what we are showing here in terms of these hexadecimal numbers, and how actually one can check that the hashes are working correctly. Is there any question up to this? Because we are running out of time, I will not prolong.
Sir, is there a reason that previous hashes are not mentioned on this btc.com and all?
Oh, it is actually not a big deal. Actually, it does not harm, but at the same time, there is it does not add any extra value also. So good observation. And this adding that actually will not, because it will take up some more space. Okay, but just by not adding it, I am not gaining anything in terms of security, or by adding it also, I'll not gain anything in terms of so ease of checking. Okay, and because it is all related to the previous hash, one can always go to the previous block and get its hash. So there is no particular reason for not including, except that it will only take up more space.
Oh, okay, sir.
Okay, any other question? Okay, so if there is no other question, I am stopping the recording.